All right, let's get right into it. Today, we're putting randomness itself on trial. And the key piece of evidence we're bringing to the stand? Well, it's none other than one of the most famous, most supposedly chaotic numbers in all of existence, pi.
You know the line, right? Anytime a pattern shows up that seems a little too perfect, a little too weird, this is the go-to response. Well, today, we're not just going to question that idea. We're here to show you why it's often just a modern superstition. I'm about to show you with cold, hard math why that excuse is, well, it's basically mathematical cope. The evidence suggests something much, much stranger is going on. Okay, so let's set the scene. Here's our evidence, our crime scene, if you will. We've taken the first 200 digits of pi and we've laid them out in a 14 by 14 grid. Simple enough, right? We just start in the middle and spiral our way out, clockwise.
Now, what should we expect to see here? Honestly, nothing. Everything we think we know about pi says this grid should be total, absolute statistical anarchy. Just noise, chaos, like TV static from the universe.
But when we actually look at it, something else happens. Something weird. A certain number, a very, very familiar one, doesn't just politely knock. It kicks the door right off its hinges. And that number is, of course, 314, pi's own signature. Now, statistically, in a grid this size, you might see it pop up once, maybe, but we find it 5 times. 5. The odds of that happening randomly, about 1 in 600. So we're already in, hey, you just want a decent scratch-off ticket territory.
Oh, but it doesn't stop there. Not even close. Because another number crashes the party. And this one is almost too perfect, too self-referential to ignore.
We also find the number 196 twice. Now, what's so special about 196? Well, 14 times 14 is 196. It's the literal size of our grid. So now you've got pi's signature and the grid's own signature showing up way more than they have any right to.
So what are the chances of both of these things happening together in the same small space? You've got the 5314s and the 2196s. Well, the probability just plummets. We're now talking about a 1 in 4,000 chance. And at 1 in 4,000, you're not just lucky anymore. Things are starting to feel a little strange. But wait, all of that's just the beginning. The numbers themselves are only half the story. Because this is where things go from weird coincidence to, well, something that looks a lot more like organized crime. It's not just what we find, it's where we find it.
See, these numbers aren't just scattered all over the place like you'd expect in a random field. No, they're aligned. They actually make a shape. They form a clear geometric structure. This isn't just a pile of coincidences anymore.
And this right here is the heart of the problem for anyone screaming chance. Think about it. Randomness makes soup. It just throws ingredients into a pot and creates a mess. Geometry, on the other hand, requires coordination. It requires a blueprint. Saying this is random is like saying you can toss a bucket of paint at a wall and get the Mona Lisa. It just doesn't work that way.
Okay, let's pause. A good skeptic, and we should always listen to the skeptics, would raise a very fair point right about now. They'd say, hey, you're just seeing faces in the clouds. This is a classic case of finding a pattern after the fact because you were looking for one.
And you know what? That's a valid concern. You stare at static long enough, you'll see a bunny. But here's the counter-argument. First, the setup isn't arbitrary. The spiral mapping is standard, and we use the bare minimum number of digits, no cherry picking. But the real clincher is that the patterns are self-referential. They're about pi itself and the grid itself, and that's a whole different ballgame. And that self-reference, that's what leads us to the smoking gun, the knockout punch, because what we're looking at isn't a few separate coincidences that happen to line up nicely. No, it's one single, deeply interwoven system.
So let's break it down. Look at that 196. It's not just sitting there somewhere in the middle of the noise. The 1 is the very first digit of our sequence. The 9 is the 100th digit, the exact middle. And the 6 is the 200th digit, the very last one. It's not a substring. It's a structural bookmark. It's baked into the architecture of the entire block.
Okay, now look at the 314s. 4 of them form this perfect symmetrical cross. But here's the truly insane part. Follow them. All 4 of them connect to, they all share the exact same digit 1 right at the dead center of the grid.
Are you getting this? That one single digit in the middle isn't just a center, it's a hub. It's the pivot point connecting everything. It connects the 196 structure. It connects the 314 cross. It even connects another pattern running down the central column. It's the keystone that locks the entire structure together.
And that is what changes the game. This isn't a bunch of separate long shots that happen to all hit at once. It's one single intricate system of interlocking parts. And when you have interlocking systems, the probability of it happening by chance doesn't just add up. It collapses into almost nothing.
Which brings us to what we can call the smoking gun theorem. The joint probability, the chance of all of this happening at once, this multi-layered, interlocked, self-referential, and symmetrical structure is vanishingly small. We're talking so close to zero, it makes no difference. Randomness just doesn't build things like this. It can't.
So, back to our soup analogy. Randomness makes soup. But when you have interlocked digits, plus symmetry, plus self-reference, that's not soup, that's a recipe. You're no longer looking at noise. You're looking at what appears to be a message.
And we have to leave it there for now. But here's a final thought to chew on. As deep as we've gone, what if all of this incredibly complex system, is just the first thing we've noticed? What if we've only just begun to scratch the surface?